Hi everyone, and welcome to the second of two videos looking at some past paper questions on the topic of atomic structure. This first question is just asking us about the subatomic particles. This is fairly straightforward, I filled this in already. In terms of the masses, proton and a neutron have the same mass, so they're given a relative mass of 1. The electron's mass is about 2,000 times smaller than the mass of a proton and a neutron. Okay, it's not 0, the electron does have a mass, but the electron's mass is so tiny that we usually don't consider it in chemistry. In terms of what they're expecting you to put here, the mark scheme is allowing anywhere from 1 over 1800 to 1 over 2000. Okay. In terms of the charges, protons have a positive charge, neutrons have no charge, electrons have a negative charge, but we do want to put in +1 and -1 because it shows that the magnitude of the charges are the same, it's just the sizes that are equal. Okay, if I just write positive and negative, then it doesn't show me that a proton is just as positive as an electron is negative, which is information that you do get if you put +1 and -1. And then the position within the atom, well, protons and neutrons are in the nucleus. That's nice and easy. This question here is asking us about relative atomic masses, but it's slightly unusual in that they've given you the relative atomic mass. Usually that's what they're asking you to calculate. So this is going to be slightly different. The method that I'm going to go through here is fairly complicated and is more difficult than you'd need to really do for a 1-mark question. But the method I'm going to show you here will work in any example. This example is relatively easy because there's only 2 isotopes and they're fairly close together, and you could do this method in a quicker way, but the method I'm going to show you here will work in any case of a question like this. Okay. So if we're going to calculate the relative atomic mass, what we would normally do is we'd do the isotopic mass of one of the isotopes multiplied by its percentage. We don't know what its percentage is here, so I'm going to call it Y. And we also would then add on the other isotope, so we do 81 times, but we don't know what its percentage is either, so I'm going to call it Z. Okay, and then we divide by 100, and that would be equal to our relative atomic mass. Well, we know the relative atomic mass is 79.9. Okay. So this becomes a bit of an algebra question, and the first thing I can do is multiply by 100. Okay, so we can say 79y plus 81z equals 79.9 times 100. So it'll be 7990. Okay. And then it looks like we're kind of stuck because we don't know what y is and we don't know what z is. But we do know something about y and z. Because y and z are the 2 percentage abundances, y and z must add up to 100. Okay, so we know that y plus z equals 100. And therefore we can say that z equals 100 minus y. And therefore I can substitute this into what I've got here. Okay, I can change this to be 79y plus 81 lots of 100 minus y. And now I can work this out. I can say, take this over here, we can say 79y plus 81 times 100 minus 81y equals 7990. Okay. If we sort this out, then we end up with minus 2y equals this, take away this. Let's just do that on a calculator to make sure I don't mess that up. If I do that in my head, there's a decent chance I'm going to get that wrong. So minus 2y is minus 110. The minus doesn't really make any sense. So if we just divide by 2 on both sides and get rid of the minus sign, we can say that y is 55. Okay. What was y? Y was the percentage of the bromine 79 isotopes. That is the answer we're expecting. Okay, so the correct answer is 55%. Okay, this method will work regardless of what the isotopes are and what the percentages are. Okay, if you had 3 different isotopes, for example, they'd have to give you one of them, and then you do a similar thing with the other 2. Okay, that is a lot of work for 1 mark. There is a quicker way of doing it, but I wanted to show you this method just using the algebra because it will work in any question like this. Finally, we have this question at the bottom. Part of it's the same as the question that we did above, so we're just going to copy the answers in again. proton has a charge of +1, neutron is 0, electron is -1. And then the number of each particle present in this ion of cerium. So we're going to need our periodic table for this one. Cerium, let's have a look. I don't even know where cerium is on the periodic table. Okay, right, here we go. So cerium, we can see its proton number, its atomic number is 58. That's never going to change, right? If it's cerium, it's going to have 58 protons. That's what makes it cerium. Okay, so protons is going to be 58. Neutrons is going to be 140. Use the isotope that you've been given. Just be careful. Don't go back to the relative atomic mass. Just be careful. Use the isotope just in case it's different to what it's got here. In this case, it wouldn't really matter, but in some other cases it would. Okay, so to work out the number of neutrons, we're going to do the atomic mass, take away the number of protons. So we've got 82 neutrons. And then the electrons would be 58, but we can see here we've got a 2+ ion, so that means it must have lost 2 electrons. So therefore I'm going to be 56 for my electrons.